Electric field line diagrams give us a way of visualizing the electric field that surrounds charges. The electric field line diagram method is used because in reality the electric field is defined everywhere around a collection of charges. And so to properly draw an electric field around charges, you would have to draw vectors at every point around the charges, which would be very impractical, and you'd have a whole bunch of vectors sitting on top of each other and you wouldn't be able to tell what was going on at all. So electric field line diagrams simplify the situation a lot and allow us to still visualize what the electric field looks like without drawing an infinite set of vectors. So electric field lines, this visualization method, the electric field ends up being tangent to the lines. So if you have a collection of charges and you have these electric field lines, you can look at any point near these lines, and if you want to know the electric field at this point, then it would be a vector that is tangent to the line. So here the electric field would be shooting off like this, here it would be like this. It's always tangent to these lines. The closer together the lines are, the stronger the electric field is. So if we look at this diagram here, we can see the electric field lines get closer together as we approach the charges, indicating that the electric field is stronger. So to draw electric field line diagrams, we need to follow a set of rules. The rules state that lines begin on positive charges and end on negative ones. This guarantees the correct direction, because we know that if I place a positive test charge near a negative charge, it will be drawn inward towards the negative charge. That's the direction of the electric field, so that should be the direction of the electric field lines. On the other hand, near a positive charge, a positive test charge would be pushed away from a positive charge. That's the direction of the electric field, so that needs to be the direction of the electric field lines. On this diagram, any test charge placed in this area would be pushed away from the positive charge, pulled towards the negative charge, and so that is the direction of the electric field lines. And that means that they end up beginning on positive, ending on negative charges. The number of lines is proportional to the charge. So in this diagram, I can tell that these charges have the same amount of charge because they have the same number of lines touching them. Likewise, these two charges have the same amount because if I count the lines, I see that they have the same number of lines touching them. And in this diagram, you can see that the red charge has twice the amount of the blue charge because if you count the lines, the red charge has twice as many lines touching it as the blue charge does. Finally, lines cannot cross. If they did, what direction would the electric field be? If you had two lines that are crossing, that would be very ambiguous as to which direction the electric field actually points. So I have a couple of apps, little applets, that show you how to draw the electric field and work with the electric field lines. So here we have a picture that shows the electric field lines for two charges. You can tell that the left particle has a positive charge of 1 unit and the left or the right particle has a positive charge or a negative charge of -1 unit. And so they have the same number of lines touching each of them because they have the same amount of charge. So I can turn off one of the charges completely, so I only have one charge, and you can see that it has the lines going away from it because it is a positive charge. If I made it negative, the lines would be towards it. And then if I make the charge bigger, I have twice as many lines. So if you have the two charges, if they're both positive, you can see that the lines can't cross, so they must bow away from each other. And I have the same number of lines touching each of these charges, indicating that they have the same amount. If I boosted one of them to have twice the charge, then it has twice as many lines touching it. If I have a situation like this where I have a negative charge and it's twice as big as the amount of charge of the positive charge, once again twice as many lines touch the negative as the positive, and the electric field lines go from the positive charge to the negative charge. Another fun applet that I wanted to show you, this is actually posted on Learning Hub, so you can try it out on your own. This is a game called Electric Field Hockey. So basically with electric field hockey, you have a positively charged puck, and you can position positive and negative charges so that the puck will move into the goal, like so. And then so once we start the game, the puck moves in response to the negative charge. And I made a goal. Let's reset. So we can also show the field, so you can see how the electric field is shaped by the charge, and this is the electric field that the positive charge reacts to. And you can also see by turning on the trace where it has gone. So this is kind of the let's just figure out how this game works level. We also have a difficulty level 1 where we have to get around some sort of barrier. Oops. Let's put the charge here. And we can start the game. That didn't quite work. So we can practice putting the charge in different places, resetting, and seeing what happens. And so it will take a few tries to get around this barrier. There's also a level 2 and a level 3, which is really tricky. So if you want, you can try that out. It's quite a bit of fun, and it helps you to see how the electric field can cause the positively charged puck to move. So next, let's look at this question. Consider the 4 electric field line patterns that are shown. Assuming there are no charges in the region depicted, which of the patterns represents a possible electric field?